Question number 2, emulsion timing. I'm going to start off with the two extremes to try to represent uh, the best and most simple following of the emulsion timing. We're going to start off, here's the main well. This is going off to the booster. My drawings aren't the best here. And down here is the jet. So right now we're assuming there's no holes in the main well. Initially, the main hole was an anti-siphoning device. That's how it started out back in 1909-ish or whatever, to make sure that the fuel was not siphoned once it got started from the fuel delivery. They put a small air bleed at the top, and that was mostly an anti-siphoning device. Fuel at that point had the ability to vaporize pretty simply on itself, had a lot of light ends in it. So today, when something like this would, just the smallest amount of air being bled into the main well, when we're finding an engine that the power level is reaching the maximum size in the fluid system, the fuel delivery part of the system. For instance, they're running I'll just pick a case where I know this to be true at times. Carburetor restricted 4412 engine that somebody's really worked on, and they have a track where it's necessary to run a lot of RPMs, and these darn things get to making pretty good power at times. So we'll say this fellow's in the top part of his research, and where fuel and air are both important, and he's maximized the size of the well. Well, if you put more emulsion in the main well, I'm not going to say you'd be this stingy with the air. I don't want to use the word emulsion at this point. You would be filling the well with air and fuel, displacing fuel that's necessary to make power. So there's a blend between the amount of air that you want to put in and the amount of fuel you want to deliver. What you would use the air bleed holes for, the main well, emulsion holes, that's the name they've been given, is to balance out the booster signal in the main jet. So you'll be adding a small amount of emulsion holes as you can. Now these channel here, there's a side channel. Today takes it up to the main air bleed. Main air bleed. So for instance, if you have an 035 hole in the main air bleed, at no point will your air going into the emulsion well exceed your main air bleed. So what you're doing is, in reference to the diameter of the holes in the emulsion well, is choosing at what point you want to disturb the fuel in the main well. When I say disturb the fuel in the main well, so you've got the main air bleed supplying air to the column that's alongside of the fuel delivery main well, and this, they're open. I'm not going to draw all the little channels that go back and forth here, just a couple. So the main channel here for the air coming in can access the emulsion well fuel air delivery. So if you just take it from one extreme to another, instead of the hole being at the top, just use for an anti-siphoning device and a slightly balancing of the booster, you take the same size hole and you move it to the bottom. No more, you take the same air bleed out of the top and just put it in the bottom. And the difference is significant. When you're looking at the amount of booster signal it takes to lift the column of fuel all the way up until it gets to this point, this is where the first axis of air is. So you have to have a fairly significant amount of booster signal to lift the fuel up the column. If you go and you take the same hole out and you put it in the bottom, now once the fuel gets to the level that the air bleed hole is at, the emulsion bleed hole is at that point you're disturbing the fuel and becomes, aerated. That's where they get the term emulsion, when you're going from one extreme to the other. As soon as that point happens, you start putting air into the fuel. Now you're filling the channel, obviously, with air and fuel, but it becomes lighter. By the nature of the mass, the air interrupting the mass of the fuel, it becomes lighter and actually easier to lift to the booster. So one of the first questions is where we put the holes in the emulsion well. Well, if you don't mind filling the main well up with air, the lower means you're going to have an earlier response to low air movement, because you're going to have a lower mass weight in the fuel in the channel. So at lower engine speeds but lower air signal, it's not lifting the column. The unfortunate part of putting them lower is at some point when the fuel delivery goes up and you're beginning to need the total mass fuel to increase performance. And some of these engines, the manifolding and such, there's so much going on in the manifolds and some of these carburetor restricted motors. Just getting the fuel into them and the air fuel ratio and droplet size is as important. It's always, the criteria. These engines aren't looking for overall efficiency. They're just looking to get some oxygen and some air in there that they can burn. And that becomes a bigger performance point than having the optimum air fuel ratio. So you have to find out what drives the vehicle's performance. But that's the two extremes, putting the same hole in the same bottom. So what you end up doing by changing and adding numbers, it has a group of things that you're doing with the most simple type of emulsion system. You're balancing the booster signal versus the carburetor's inherent resistance to moving air. So you've got booster signal, air movement, and then you're trying to work within that to optimize the jet size so that you'll over the range of the engine be able to get the best performance. One of the problems with this early style system, and this is why I always resist the certain words, like I say, emulsion. I had done a clear view of main wells to show the difference in when I first got my first patent, which I'll show some of it here, on what we thought was emulsion, and so you can visualize it. And what ends up happening is the fuel comes in the main jet, the air comes in the side that the air bleed goes in, and there's nothing in there to disturb or cause it to stir or anything. So it just basically stays stratified, which means the fuel stays on one side and the air stays on the other side. And the more air you do, the more it just pinches out the fuel. The only time it's really effective is when you have low signal rate, fuel's coming up, and you're disturbing the balance of the fuel going in, the weight, and you're causing it to aerate the fuel at that point. And then once you pick up speed and it wants to separate again and go stratified. So that's really, when you visualize this and you try to look at it on a more scientific thing, what you think is going on inside of some of these is actually not. Our patented system, you got the same main well, and inside the main well, we do it in the preferred method, which is, we don't even use the preferred method yet because all the other methods are working so good, is a series of ribs. And how do we put these ribs in? Most people know we use different taps, thread per inch, and they have different depths. So at the rate of consumption, when the air comes in, I'm just going to go over here and make the weight. This is the air bleed. And the air comes in from the main air bleed. That once the air goes in here, it has a tendency to want to stir it over each of these ribs. So you're getting sheared fuel. So it's much like cascading waterfalls. So if you got a group of waterfalls, and you're putting fuel over it, and you keep going over it, it keeps stirring it, and as you increase the consumption rate, it begins to, make a froth. Then when you finally get to the maximum mark of ranges, you're getting the frequency of the air and fuel breaking up by the sound waves. So you're actually disrupting it. So the speed gets up, and eventually the air over this, you're getting another a reverberating wave in there from it's like a tuning fork. The air going over here tends to set up vibrations, and that further breaks up the fuel. So in this case, it's about the shearing. We're shearing fuel, so both sides would look something like this. I'm just drawing it horizontally now. So the fuel would enter here and stir and shear. So at the rate of consumption, it's able to shear the fuel droplets and make them pretty small. Actually too small in some cases. We had to go back and make them a little bit larger. But that's the inference on the shearing that we use when we have our 251 patent. If you looked it up, it's about shearing fuel in the main columns. Normal one is smooth conduit, and ours could be anything. We took and patented everything that wasn't smooth wall. So that's the beginning. I'll try to elaborate a little bit more on the emulsion timing in just a moment. I just want you to think about the fact that now it's a collaboration between the fuel delivery at the main booster, the internal resistance that's offered by the flow system from the jet all the way up to the booster. And that's why I say a lot of people don't understand it's a system-wide approach now. Our booster banjo has a 250 ID in it, because it's the same thing as I pointed out in here. At some point, if you're trying to get the fuel droplet smaller in the main well to deliver it to booster, the last thing you want to do is recollect it in the banjo stem. You go through all the trouble of shearing the fuel down, and then you close it back down into a 140 banjo stand. It just defeats the effort. So the engine is looking for hydrocarbons and oxygen. How you carry the mass of fuel, the engine is less related to. The Pro Stock engines that I was tuning, we were currently on our killer most runs looking for 13.8 or so, which is fairly rare. Most people can't run them that efficient without having other problems. I like to say burnt piston, but certainly, developing an early pressure and getting a lot of heat into their piston assembly. But once you start having the point, like in our case, we have the repositioned venturi in the carburetor. I'm going to draw a picture here. It's not, actually make venturi. And the booster's below it, adding currently, we just checked the other day and we let you know it's about 80% more than a standard carburetor for the fuel delivery. And we have shearing going on in the main well. This is a quick picture. Now what I want to do, because I have plenty enough booster signal, is I add a ton of air. Our average air bleed on a high speed, on a 2400 we just delivered, so it's just checking, one of my customers called up, it's a 046 on a 2400 butterfly. And I'll have 4 is a standard issue. These are 035 main well air bleeds, and that adds just one heck of a lot of air into the shearing process going through the main block, metering block, because the engine is looking for hydrocarbons. Also, as it making the fuel lighter, it actually makes it easier for these, even though it's a 2400 butterfly system, it's very little air going through each of them. It actually makes it easier for it to lift that very light column in the fuel. So when you're looking at aerating, shearing, and trying to deliver the fuel, it's a system-wide approach. So I hope that gives a quick answer to the number 2 question. Please, if there's more that needs to be done, I'm open to hear it. Thank you.